A couple of years ago, I had the opportunity to contribute to a trading platform that we built in the Ruby language. And most of the hard lessons learned there will drive the content for this talk today. For our agenda, we're going to first look at system calls and how we access resources from user processes, and eventually look into file descriptors, their behavior, and also the fundamental differences between blocking, non-blocking, and asynchronous I/O. With the Reactor Pattern, we'll look into how that facilitates event-driven I/O as well, and then eventually move on to a section where we look at patterns, gotchas, and best practices, which is applicable to both new users as well as advanced deployments. So as with most things in life, you can never walk, you can't run before you walk, and all the patterns presented here, it's framework agnostic, meaning it's transferable to Node.js, any event-driven frameworks as well. And for brevity's sake, we'll keep things really simple and just focus on reading, writing, and connecting. Whoops. So could I have a rough head count of how many people are using any of these technologies in production at the moment? Okay, are developing against them? Who's just here to learn? All right, seems fair. So the sweet spot for the Reactor Pattern is soft real-time systems where throughput is much more important than processing. So what this means is that for any given process, there'll be a large amount of in-flight I/O. And the load pattern for these processes is there's a very little CPU time per any user request. And what we'll try and do is then drive I/O through a single core and try to maximize that core and just doing work and not waiting on any I/O. However, it's never about the speed of a single client or a single request, which is, you often find this on mailing lists, in blog posts, and on Twitter as well. Someone upgrades the application to an event-driven framework, and that's completely doing it wrong, because the goal here is to maintain acceptable response times for more clients, preferably with the same or less infrastructure. And the example application we're going to use throughout this talk is the relationship between a broker and different trading terminals. So what is the protocol we're going to use as well is what very popular in the financial services industry. It's called, or acronym for Financial Information Exchange, which is a really, really compact wire protocol to facilitate things like high-frequency trading, etc. And is an example of such a fixed message where it's basically a tagged value protocol. And you can pack an enormous amount of domain information in a small chunk of data. Now, dropping back to the system level, on the one hand, we have the kernel, which mediates access to everything that our user programs could need, I/O, memory, CPU. And our user code is always basically anything you can deploy runs in user mode. And that's for security and stability requirements. Now, we access resources from our user code through the kernel using system calls. So, as an example, it's basically the signature is mostly like a normal function call that you'll be familiar with. This example, we tried to read 4,000 bytes into a buffer from file descriptor number 5. Probably a better way to explain this is look at the diagram, and we have two Ruby processes that's trying to read from disk through the kernel. So the best definition I can come up with for a system call is it's a protected function call from user to kernel space with the intent to interact with the system resource. Important characteristics here, it's a uniform API across many different systems. So modern Unix systems, Linux, BSD, etc. That same function prototype, it's cross-platform. Behavior, however, changes from platform to platform. So the send file is a pretty good example of how this is, the behavior is not always the same. And some operating systems that do not support something natively they'd still support the call, but they have a slow emulation for it. Performance-wise, there's two things we need to consider here. They're much, much slower than normal function calls within the same process, 20 times or more, even for the very, very simple operations. And there's a definite context switch involved with doing that as well. We're swapping out memory references. We're swapping out CPU registers as well. And probably the most important for us here today is that they can block. So if you're doing a read call on a network socket that we're expecting data from a downstream client, and we're on a slow network or the upstream peer is slow, then we're going to block indefinitely until that data we're expecting to arrive is there. So who doesn't know what file handles or file descriptors is? All right, that's good. So if we invoke in the open system call for a local file with the intent to read that, we'd get back a numerical reference. And a file descriptor can reference a local file, a socket directory, pipes, and the API for that's always consistent. So we just, in our system calls, we only care about that numerical reference. We don't care what the underlying device is. So it's very easy for the programmer to use it. And the definition for this is a numerical handle that references something allocated in kernel space. And for network transfers, we're concerned with buffered I/O. So we have a buffer in both the kernel as well as the user space. And by default, all file descriptors are blocking, meaning if we intend to read a chunk of data from a descriptor and the buffer state is like maybe the watermark at this point is halfway and it's not enough data to read, then we will block looking at that from more a visual perspective. So we have a function system call that's trying to read 4,000 bytes back into a buffer, but the kernel buffer at this point only has 1,000. So until that fills up with all the 4,000 we need, we're going to be stuck in a block state. Nonblocking I/O, on the other hand, allows us to change the behavior of file descriptors by setting a flag on the socket, the non-block flag. And what happens here is that read request would then only be initiated if the system call won't block. Otherwise, we'd raise an error condition, depending on the system you're on, E again, or E would block. However, it's only a guideline ever. You're still invoking a system call. It will just tell you, like, hey, this particular call would block, but there's still the context switch that you pay for. And it's also not supported by all devices. So non-blocking semantics on local files is a no-op operation. However, non-blocking I/O is also not asynchronous I/O, and this is something a lot of people confuse all the time. Actually, the big irony here is one of the best async I/O implementations is on the Windows operating system, a subsystem called Windows I/O completion ports. On Linux systems, we'd have extension of the POSIX specification called the real-time extensions. Now, there's two things with async I/O that we need to remember, and none of them is really applicable to network I/O at all. They often skip double buffering. So the moment we want to read something from a file, we'd allocate a buffer in our user space, and we tell the kernel, go out, do work. When you're done with it, put the data back in here. So there's no transfer from kernel buffer to user buffer. And the other issue is it only supports file I/O. So it's useless for network connections, and it's really only popular for database systems. Oh, man. Oh.
Press escape.
Yeah. Okay. Sorry about that. So to recap, non-blocking I/O is, or the non-block flag is only a guideline. It's still invoked in user space. Whenever we want to read data, we read data in user space as well. And moving forward, we prefer the terms blocking and non-blocking I/O. We not refer to async I/O at all. So remember, the primary use case earlier for the reactor pattern is increased throughput, which presents us with a number of challenges where we need to work with a large number of file descriptors. We need to be able to respond to their state changes. So we need to know when whichever subset is readable, whichever subset is writable, and then execute our domain logic against that, while maintaining acceptable response times for all the other clients as well. Remember, it's not about a particular single request, but about servicing lots of different clients. So at a very low level, a very high level, sorry, the reactor pattern can just basically be presented as a infinite while loop, where we do two kinds of work. We add new file descriptors to this when we receive new connections, and the most important one is, for example, the modify descriptors methods with which we get notified from the kernel when there's work to do or particular error conditions when a connection's been disconnected. Probably a better way to understand this is looking at this diagram where we have the loop ticking around all the time, and we've got a bunch of descriptors registered here, and they're in various states of read and writability. Who's familiar with selects, epoch? Okay, a couple of you. That's good. So Multiplexed I/O is there to solve a particular problem, because non-blocking I/O is extremely inefficient. Every time we try to do I/O, try to do a read, and we get an error response back, then that essentially is polling. And so a good way to look at multiplexed I/O is its concurrent blocking. So with epoch, for example, we can put tens of thousands of file descriptors. We can tell the kernel, hey, monitor these. Whenever something changes with them, let us know about them. And again, the separation between what happens in the kernel and what happens in user space. So and the kernel space, or the multiplex framework always lives within the kernel space. And in this example, we've got an I/O-bound application where in user space that has a bunch of file descriptors registered with the multiplex framework. And the canonical reference between what happens in kernel space and what happens in user space is only that numeric reference, the file descriptor. So we have to register it both with our event loop as well as let the kernel know in the multiplexer, inform us when the state changes over there. So we'll just go through like 4 or 5 different steps and see how this works. So the first would be if we want to register 200 file descriptors with the multiplexer, that will be step number 1. And then after we've done that, we continue doing work. So our while loop or our event loop keeps ticking along until at some point we get woken up by the multiplexer when the state changes. So there's a subset of the descriptors we registered. Oh, of the 200, maybe there's 10 ready to read and there's 20 ready to write. At which point we can ask, well, which subsets do we need to do work on, and then proceed to actually do the work on them. Just to step back for a second as well. So these notifications or state changes in readiness for reading and writing, these are the events in event-driven I/O. And these are handled in our user code through callbacks or event handlers. However, a reactor pattern only provides I/O concurrency. This is no guarantees that any user code would execute concurrently in any way. They all execute on the same thread within the context of the while loop as well. So that's the reason why callbacks and why user code and why they should have minimal CPU per request, because every time you spend a lot of time in a callback, we're denying service, we're blocking our current client, we're denying service for everybody else. And each turn through the event loop we refer to as a tick. So it normally can do several thousand of these per second. And each tick through the event loop is a time slice, an opportunity for doing work. And each of these ticks should use a minimal amount of CPU time. So before we move on to the next section, there's a minute or two for QA regarding this lower level stuff. So is there any questions at this point?
When you mention that tick, does that also mean, when you say time slicing in the tick, does that mean that your handling code also has to do?
Yeah, it's both. It's both. Oh, yeah, sure. So he was asking if the tick is just user code or work in the Reactor you need to do as well. So yeah, it's both. We need to do work. We need to do transfer as well. So we just get notified like, hey, there's data to read here, but the read still happens in user space also. So it happens within the context of the while loop, and the same with the callbacks as well. So there's work, definitely time slicing between the Reactor as well as whatever callbacks and stuff are registered as well. So yeah. Any more? OK. So the first thing that trips people up a lot is confusing different layers. And the only one that we should mostly be concerned with at this point is the application handler and dispatch handler in the top, which is fed by the multiplexer. Multiplexer feeds the dispatch handler, which feeds into our domain logic. And the dispatch handler, which is sitting in our Reactor framework, is responsible for handling very low-level events. So it'll respond directly. The multiplexer will tell it, hey, you can read this. It will respond to those very low-level events, which may not be of interest to our application or our domain logic at all. And it also wraps anything that's not operating system agnostic. So if you have weird edge cases with reading and writing, then that'll be abstracted at this layer. So a user code doesn't have to worry about it. Other responsibilities include buffering, transferring data, and because we're using Eventmachine, for example, in Ruby, the data coming off the wire would be converted to Ruby strings when on receive, and also converted back from strings to a stream of data when we're sending data back out. A code example of what this would look like, it's a very command-driven tell-don't-ask interface, because when the multiplexer tells us to do work, we need to do that work as fast as possible. You can't ask any questions. In contrast to application handlers, which is our domain layer, which is where we implement most of our business logic, or the very thing that makes this particular service unique. And the events here is also much more high level, where it's connection accepted, connection read, the things that we want to respond to in our user code. And a large responsibility, in addition to just business logic, is protocol parsing. So if we have a service that works with JSON data, we only get raw streams of data back all the time. So we need to know where our boundaries are, where we need to parse it, etc. We'll get to a section on protocol parsing in a bit. Code interface, again, it's just callbacks, like we mentioned earlier as well. So and the other thing with these callbacks as well, it's an so we can modify them quite easily by extending these interfaces. So if there's new events that the new events that the Reactor introduces over time, we could just keep extending these interfaces. Quick note on glue. It's something I noticed in a lot of projects as well, is where you have callbacks, or a lot of people implementing the whole application inside callbacks, where you should encapsulate, if there's a complex protocol or you have complex business logic, to encapsulate that somewhere else and just use your connection callback handler for delegation. Number 2, testing. You don't need a transport to test anything. So at the top there, we have a simple connection callback definition, where we just receive data. When we receive data, we enqueue it somewhere else. Now, for the purposes of developing against these frameworks, we can always at all times assume that the framework will know how to manage its data. We just get a pass from the network. And when we test it, we can stop these interfaces out pretty easily as well. So on the bottom, we can say, well, receive data with following stop data, and just do the assertion afterwards that the data that we've received have been enqueued. Confusing synchronous and asynchronous layers. So the events or state changes to file scripts always occur at the kernel level, but we get notified. So it occurs at the kernel level, but they're handled synchronously, as addressed through his question earlier also. Just referencing back to that diagram. So bottom 2, definitely kernel space. Top 2, definitely in user space. And we have 2 options in dealing with deferring work here, or to ensure we continue servicing clients. The first one is to use a background thread pool, which is provided by default per Eventmachine, where we can take work that is CPU bound. We can defer that. For example, if this message was pretty expensive to parse, we can just defer that parse from the background thread, and we won't affect other clients we need to service. Or we could schedule this on the Reactor thread as well. So coming back to the tick principle again. So every time the while loop goes around, the first thing we do is we service I/O. We handle other clients, and then we do user work. So every time we schedule work on a tick, once this has gone around a couple of times. So it means that for this connection, this callback's called on tick number 1. And then we say, well, we don't want to do the work right now. We service I/O first for other clients, and then we continue. And we schedule this callback to run on the second one. So gotcha number 4, too much time on CPU. So that while loop, or the Reactor loop that we had earlier, it always only ever runs on one core, on a multi-core or SMP system. So if we block that core, or we spend too much time on CPU on that core, then we're blocking the whole loop, which is fundamentally against the principle of time sharing. First problem that I see a lot is tight loops, where you have work to be done back to an enumerable. And every time we walk through this, so until this whole sequence completes, we holding CPU resources that can be used to service other clients as well. So a better way to do this is to use a tick loop functionality. Now with the tick loop is we'd go through, we'd pop off work, and then after we've first done like a tiny bit of work, we'd go around again. So that amount of work gets scheduled on on the next tick. So it allows I/O to run, we do the work, and this process just repeats until the whole array is empty and all work's been done. Back to the protocol parsers. So that's one of the reasons why, for example, Mongrel has a custom extension for parsing HTTP headers, because we pay, if you have a slow protocol parser, you pay a cost on both sides. You pay a cost when receiving to parse it, you pay a cost when sending data back out as well. So my recommendation here is whatever protocol you're using, if you have a JSON service, if you have a custom HTTP server you're writing, always try and use a fast C extension for parsing this protocol level information. And name resolution and connect. So normally, in relation to the overhead of a read and a write, whenever we establish connections, we have things we need to be concerned with, like sometimes authentication, handshakes, etc. So there's a lot more going back and forth than just a simple read or a write. And the same thing with DNS, which is something in most systems that's often overlooked, where, so in this example, assuming that that connection request to slowbroker.net is going to take 20 seconds to resolve, then we're blocking that event loop for 20 seconds until that resolution is finished. The better way to go about with this is to use an async resolver. So we just invert control here, where we ask the resolver to resolve a particular address. We set a callback on that, where we get the addresses back of this particular name resolution request, and then we take the first address and then do the connect. So even if this takes 20 seconds, that's okay. Other clients can continue doing their work. Same thing with async HTTP APIs. So if we're interfacing, for example, hitting endpoints like Facebook, Twitter, etc., and we know that we're going to do a lot of work, we're going to be doing multiple requests, and always try to use keep alive just to negate the connection overhead, especially in the context of the event loop as well. So as I mentioned earlier, not all file descriptors support non-blocking I/O. Local files, for example. So there's two problems here. The first one being cloud computing. EBS volumes have very variable performance characteristics. So the fact that reading from a local file that has a non-blocking flag set, the moment we want to read from it, it will always tell us, hey, you're ready to read this data. But it could be that that volume at that point is overloaded. So we might have to wait 10 milliseconds. We might have to wait 20 milliseconds. The same thing with using slow disks. So we don't account for mechanical movement if we're referencing stuff or reading anything on a tape drive, etc. So so a while ago, I spent some time and wrote a Ruby extension called against the library called libeio, which powers the file system module in Node.js. And it's extremely callback driven. So all of these normal APIs that would block an event loop, like open, closing file descriptors, that's another thing that can block for quite a long time. So what happens here is all this work gets scheduled on Reactor threads, but more on a lower level. And we're able to eventually just schedule this work off, give it the callbacks, and we're able to continue serving clients through our event loop. All libraries that you're using have to be evented. So there's little point in having a high-performance reactor, but then introduce like blocking calls. So the first one is an example from Redis, for example, which is not that big an issue because it's a fairly fast interfaces, etc. But again, it's just a callback-driven interface. A better one is MySQL. If you've got a query, and this query is going to sleep for 3 seconds, and if we run this synchronously through a normal synchronous MySQL client, then that's 3 seconds that the loop's not doing any work. So our service is basically blocked on this one particular query. Whereas if we're using an invented interface, we fire off the query, we give it a callback, and other clients can, again, continue doing their work. And when we get the data back, we could just use that. Number 8. So Ruby is a language, scripting language, where we don't manage memory ourselves. So meaning that we need to be careful with allocation patterns in our callbacks. If we're just going to be allocating a bunch of stuff, then we need to be aware that the GC can be evoked at any time during these callbacks. And the GC cycle can block, depending on your heap size, anywhere from 50 milliseconds to 100 to 130 milliseconds. So my recommendation here is be careful with sloppy allocation. And there's also facility exposed through Eventmachine as well as other invented frameworks called connection proxies, where we might have a situation where we're getting data off a network and we'd like to stream that out to a file. So we have two file descriptors that registered on the loop. We can, on establishing a connection, we can say enable proxy for this connection to the other client. And what we can do at this point is then stream data from one descriptor to another, but the data being transferred there happens at the reactor level, so it never actually goes through Ruby. It doesn't get allocated on the heap. There's no garbage collected pressure at all. Number 9, buffer sizes. So most of the work that you'll do in network services, there will be TCP/IP stream-oriented protocol, and on most of these callbacks, the buffer would be 4 kilobytes. In some cases even larger. So coming back to the fix example that we had earlier on, you can pack an enormous amount of domain information in 4 kilobytes of data. And the same thing with sending data out as well. Usually when we send data, it doesn't automatically go out. We have a send buffer as well. So people often confuse situations where they try and write one character at a time out, and it's not coming out on the other end. It will only go out when the buffer fills up. So the recommendation I have here is when you have really compact protocols and you receive lots of them or a big chunk of data to parse, then try to do boundary parsing where most of them you'll know this is the start of a header and this is the footer of a message. Split them up like that and then parse them using the next stick interface where we schedule a particular message to say, well, go around again, service other clients and do the work on the next stick through. So the takeaways from this talk is this pattern is particularly good for time sharing for IO-bound services. If you have anything that needs CPU time, it won't work. And it's one of the things, or very ironic with using thin or event-driven services with Rails, because it's really only useful if you have everything in your stack that is using evented I/O as well. For example, template rendering and a particular Rails request, it might be 200 milliseconds, but that's, again, it's blocking a loop. So it's the complete wrong use case for using any of these technologies, even though a lot of people are using that in production. If there's someone want to talk to me about this afterwards, we can maybe address some of this in QA. I think I've gone through most of this too fast, so that could be interesting. And the system calls are expensive. Be aware of them. Also know the difference between blocking and non-blocking async I/O. Just forget about async I/O for the time being because it's not useful for any of this work being done here. And always try to schedule work through ticks. We're never the only request. We're never the only client. Respect the neighbors as well. And as long as we keep doing work in our application layer, so be aware what happens at the dispatch handler, but only worry about your app handler. Don't confuse any of those. And last but not least, always focus on interfaces first, because the data will come either from the framework in production, or you could stop it out in testing. And yeah, so I guess it's time for QA. Yeah.
So clearly with examples like your MySQL example, you wait for the query and to get a callback.
Yeah.
Clearly for any other compute-bound task you might have, one could use a similar pattern. Does the Reactor Pattern or Eventmachine offer an ability to make it easy for me to go to another process and do a non-blocking call to that?
So what you can do, So he was asking if it's possible with a MySQL example to do the same thing with compute-bound work. Is that correct? Yeah. So Eventmachine exposes, well, we can answer it in two ways, depending on the Ruby platform you're using. If you're on 1.8, then it's not going to be as efficient as doing a 1.9, depending on the CPU work you're doing. But it does expose a thread pool interface that you can use. So the API is eventmachine.defer, and you can pass it a block, and that block of code will then run in a thread pool. I think it spawns up to 20 by default, so it'll run any of those threads, and then eventually when it gets back, you can give it a callback as well. If it's I/O bound, so you can also do the same thing if that particular query were to do I/O. So you can also put it back in the background thread, but there's an important consideration here. The default MySQL gem, the one, not MySQL 2, which a lot of people are using at the moment, that one's okay, because it respects the Ruby interpreter's semantics for switching threads. The other one, or the default one, which I think some people might actually still use in production, so that blocks the whole process, regardless of which thread it's on. It doesn't know when Ruby's switching a thread, so the extension's not properly written. In that case, you won't get any benefits from even deferring I-bound work to a different thread, but for the compute-bound case, yes, you would. And on 1.9, that will run on a different core as well, and not on the same core, which on 1.8, it's only green threads as well. Questions? More? Yeah.
Is select considered an asynchronous way to get data from descriptors, or is that considered non-blocking?
Well, it's a multiplex framework as well. So yeah. So you're just asking if select is a way to do non-blocking I/O as well. Yeah. So select, it's just, I mean, with all of these multiplexing interfaces, select is probably the most portable one. There are some emulations on that available for Windows as well. And the only problem with that is it works. If you've got a small amount of descriptors, so if you've got 10, 20, that's OK. You can use select. You don't need to use any of the more high-performance EPOL or KQ. So with the select one, it's a file descriptor that's not blocking. It's not the multiplexer. The multiplexer only allows us to register and to tell them, well, for this descriptor, we're interested in these following events. So it's not that select. It's just an implementation of a multiplex framework. Sure.
How well supported is Eventmachine on Windows?
Not too well. There's a lot of edge cases at this point still, but I know like a lot of guys are using it actually for serial port interaction. So they'd have situations like warehouse applications or terminals, and they need to use serial ports for that, etc. So that's probably the best use case I've seen for that. There's one or two guys that use it all the time. I guess they're just pretty much into pain, as always coming back. But yeah, so definitely there's work to be done there. There's a JRuby implementation as well, a JRuby Reactor, which probably would be a better fit to use on Windows platforms.
You went over it, but just to be clear, what are some good examples of when to schedule work for the next take-home reactor?
It's if we know that we're going to use, I wouldn't say like a lot, not enough CPU to warrant in queuing down on a thread, but you know that there will be some time spent on the next, there will be some CPU time spent, and if we know that at that point we probably have a lot of connections, then it's better to use a tick, and just to be sure that we'll go around, we can serve other, we can handle other IO requests as well, and then do our work there also. So that's what I recommend, yeah. More? Sure.
I was wondering, basically the differences between using run versus defer versus schedule versus next. Like there seems to be so many ways you can use it, and I've been using it like wanting to explore where I can use this different.
Yeah, so interesting that you mentioned the schedule one as well, because schedule at this point, it's actually just a wrapper for nexttick, and like one of my coworkers, he's one of the core committers to Eventmachine, and we were talking about it the other day, where we actually just want to flatten the whole thing out and just have two APIs, defer and schedule, or defer and nexttick. But it is confusing. There's definitely, it's one of the reasons why I chose some of that for this topic as well, because it tends to confuse people. Like I go through the list from time to time and just look what is being posted, and that's definitely something that bubbles up all the time. Yeah.
In general, this seems really unnatural, and particularly that because Ruby doesn't necessarily handle coroutines natively, that if you're trying to do this, why would you try to do it in Ruby as opposed to a language that actually supports coroutines natively?
Yeah, so he was asking, why would we want to do this in Ruby that does not have native support for coroutines and not a language that do have? So I'm not sure how much this was covered in the previous talk, but there's a native fiber implementation or a native coroutine implementation on Ruby 1.9, which is what a lot of, I chose not to cover this here because I consider that to be an anti-pattern most of the time. So the link between a user process and what happens in the kernel most of the time is only like an integer reference, right? So it's really small memory allocation. Now, what happens with coroutines is, especially in the Rails context, so you'll stack after a particular request, your stack frames, I think it was covered in RailsConf a while ago as well, is 60 to 65 stack frames. Each stack frame is 4 kilobytes big, yeah? So coroutines start off pretty small. They, I think, a default stack size of 4 kilobytes. And then eventually it grows up to this like enormous amount of state stuck there. And if you're spawning, say you have a fiber pool or a coroutine pool of 20 of them, then it's not only, that'll just be for the connections to get to the HTTP request, but obviously what people do in this case is they have fibered connections for MySQL, fibered Redis connections, fibered other connections. So you're sitting with like all this memory state stuck in this one process. So what happens is the references, so it becomes expensive to keep track of state in user space for what happens in the kernel space. So there definitely is opportunity to do this. 1.9 is a lot of libraries available for doing that, but I consider it, given that one of the biggest problems with the Ruby language is actually the garbage collector, and the moment that you do that, you're putting pressure on the GC. So it's kind of like, it's a nice pattern, but it defers, it delegates a problem somewhere else. And you'll notice that benchmark numbers as well, it might have twice the improvement, but it's even a much more unnatural model and assumes a lot of knowledge of these things to use that in production code. So given, from what I've noticed, the job market in the US at the moment, like if it's a really specialized application, that's okay, do it. But if it's something that you need to support through a team of developers, then the onboarding process is set to become really important for doing that. Sure.
I noticed that Eventmachine says it runs on JRuby. Since the JVM has a better garbage collector in many ways, does the Eventmachine show, like, does it handle multiple fibers better on that right now, or is it?
Yeah, so the JRuby reactor at this point, he was asking if the JRuby reactor would be a better platform for using this as a fibered model. So the JRuby reactor needs some work as well. I know that another core committer spent some time a while ago where he was actually doing benchmarks and seeing, well, how far he could push it by doing 10,000 connections, but like really high throughput. And what he found is that his JVM processes grew it to 500 megs to 1 gig, which is the same problem as I mentioned earlier as well. The references just become so large, and it's all about scalability. It's all about having more clients and not necessarily speed. So the moment, if you keep that reference small, then your ability to scale up from 10 to 10,000 to 50,000 connections, it's quite doable. But the moment you have either like a context with stack frames or like really large objects, then obviously the moment that happens, your process will grow. And also with Java, 500 meg or a gig heap, it's not free for GC either. Sure.
There's a paper, I don't remember, I have a paper with me. Essentially, what these guys did was they basically implemented CPS natively inside of the Sync file. So they were basically able to do kind of transparent coroutines, and they were able to basically simulate over 70,000 threads inside the Sync process. So I guess what my original statement was about if you really needed to do stuff like this, Ruby might not be the best place to try.
Correct. However, what I've noticed in most companies is they'd have like a Ruby team or development team. They have a product startup. Eventually, there's a requirement to have some backend services implemented as well. So obviously, you'd want to probably reuse domain knowledge in your team. And I think that's like the sweet spot for these things. So yes, you could go the Twitter way. You can move to Scala. You can do different things. But I mean, most startups, or I'd say almost everyone in this room, is not anywhere near that scale. So you can push an enormous amount of data through this as well. So we actually had a benchmark at work the other day where we could push more data through HTTP interfaces using Eventmachine and pipelining than you can do with Nginx. So it's possible to make it fast. You just need to be aware of what you're doing in the user space, what is happening in the kernel, but you can still push it pretty far. Yeah.
How do you know if you're putting things together and you think most things are non-blocking and not blocking the reactor, and then you accidentally do something that is going to block the reactor? Is there an easy way to know that you just kind of screwed stuff up?
Yeah. So the experience we had on the particular project was that we relayed lots of data to different queues, and the way there to see is just one queue gets backed up pretty fast. And that's the requirement. I mean, when you're working with this, you assume that there's a couple of core patterns, a couple of core principles, and you just try and stick to them. But it'll immediately be apparent either. Again, if you've got good monitoring in production systems, you know when certain things are going high, you're spending a lot more time I/O waiting in a particular process, then you will know. If you're not monitoring, then yeah, it's difficult to do. Sure. More questions? Okay. So I work for a company called Wildfire Interactive, and at the moment we're looking for Rails, Ruby, and specifically QA engineers. So if you're interested, you're looking for something fun, something exciting, then catch me in the hallway or apply at the URL at the top. If you enjoyed this talk, even though maybe it was a bit too fast in the beginning, but follow me at Method or fork stuff on GitHub, same reference as well. Thanks.